Hey everyone, welcome to the learning about equilibriums. So the the goal today is to learn how to find the equilibrium concentrations of a reaction. If you're just given the K value, the equilibrium constant, and your initial concentrations. So I'm going to go through and kind of run through an example, and we're going to be using something called a Rice table. Now, some people are going to say Rice table. I've heard of ice tables. It's the same thing. You might hear Rice table, you might hear ice table. I've learned it as rice, so that's what I use. So let's do this. So we talked before about K's and Q's. K being your equilibrium constant, and Q being your reaction quotient. The K is the products over the reactants, concentrations raised to the power of their coefficient during equilibrium. And Q is that same thing, products over reactants, the concentrations raised to their coefficients at any other time. So we can decide, okay, if Q is less than K, then that means the reaction is going to move to the right-hand side. It's going to move forward and create products in order to raise Q and become equal to K. If Q is bigger, it's going to make reactants. It's going to go to the left-hand side and lower down and then become K. And here's a little quick question for you. Now, this is the scenario that we're going to be dealing with today. So we have an equilibrium. Hydrogen gas plus fluorine gas is in equilibrium with hydrogen fluoride gas. Now, we're going to use concentrations for this just because it's a little bit easier. We have our K. They're going to give us a K. Fantastic. Or maybe you did some experiments earlier and now you know your K value. Cool. So now we have our K value. And we are going to start out by adding 3 moles of each of the gases into a 1.5 liter flask. Now, so real quick, we need to figure out what the concentrations of each of these things are going to be. It should be pretty simple. They all should have the same concentration because it's the same number of moles and the same volume. So we're going to grab ourselves a calculator. Okay. Pretty easy here. 3 moles over 1.5 liters, 2. Great. We know that it's going to be 2. Let's go through and write our equilibrium expression for this guy. Products over reactants, concentrations raised to their coefficients. So it's going to be the concentration of hydrogen fluoride squared products raised to the power of their coefficient. That's going to be on top. On bottom, it's going to be the concentration of H2 raised to the first power. Concentration of fluorine gas, F2, raised to 1 because it's a 1 coefficient here. Cool. And we know that this is all, if this is an equilibrium, all of this is going to be 1.15 times 10 to the second power. Okay. So right off the bat, we know a little bit about this. It's a big number. It's bigger than 1. So we know that in general, hydrogen fluoride is going to be the major part of this. It's going to we're going to have more hydrogen fluoride than we are anything else. Okay. And we can double check that. Okay. So we know all of this is 2 molar. Let's find the reaction quotient Q. Let's find the Q there. So we take that same thing. So it's going to be the initial concentration of hydrogen fluoride, 2 squared because of that. And then the concentration of hydrogen fluoride, or hydrogen gas is 2. And the concentration of fluorine is 2. So 2 squared is 4. And 2 times 2 is 4. So my Q is 1. my Q, this is my Q, my initial stuff, ratio, my initial ratio is 1. And we want it to be 1.15 times 10 to the second. So we need to raise Q up. So we know that we're going to be making products. We're going to be going this direction. So number 2, we're going to be going to the right on this reaction. And the question is, what is the concentration of each of these things going to be when it hits equilibrium? This is something that's going to be very useful to know. I mean, how much hydrogen fluoride is going to be in the container? Hydrogen fluoride gas, once it hits water, it becomes hydrofluoric acid. Very dangerous stuff. Not cool to mess around with. So I would like to know how much this stuff is making. So how can we figure out at equilibrium what is the concentration of each of these things? All right. And the way we're going to do that is by something called a RICE table. RICE is an acronym. It stands for reaction, initial concentration, the changing concentration, and then the equilibrium concentration. So there's a couple of things that we know about this. So we know the reaction, right? It's going to be H2, hydrogen gas, plus fluorine gas, going to hydrogen fluoride gas. We also know the KEQ, so I wrote that down here. I know my initial concentrations, 2 molar apiece. And now we can start filling out the rest of this table with things that we know. Now, we know the reaction is going to be moving this way. So the equilibrium concentration, whenever this thing is all done, for these guys, for hydrogen, the equilibrium concentration, is this going to be more or less than 2? We know it's going to be less because this is a reactant. We're going to be losing this stuff. We know that the change is going to be some kind of negative number for this guy. And I know it's going to be some kind of negative number for this guy too. These guys, the hydrogen fluoride, is going to be going up. So I know this is going to be a positive number. Now I don't know what this number is. Okay, so I'm going to put an X here. And I know that the stoichiometrically, if this goes down by 1, this guy also goes down by 1. If this goes down by 2, this goes by 2. So if this goes down by X, this guy also is going to go down by X. Right? And stoichiometry here, if this goes down by 1, this guy goes up by 2. If this goes down by 2, this guy goes up by 4. And so if this goes down by X, this guy is going to go up by 2X. Now, the quick and easy way of doing this, that's kind of the explanation behind all this, but the quick and easy way is for the change, your reactants are going to be negative and your products are going to be positive, and then just take your coefficients and put it in front of your X. We don't know how much it's going to change, but I do know that this product is going to, because of the 2 coefficient, is going to be twice as much as anything with a 1 coefficient. So we can go through, and now we have that change in there. I know how much it's going to change by, or at least I know I can say it's going down by X. I don't know what X is, but I know it is going down by something. We can use that to go through and write some form of an equilibrium concentration. So I know it's going to start at 2, and we're going to subtract it by X, and then it hits equilibrium. So at equilibrium, it's 2 minus X. And this one's going to be 2 minus X. And this is going to be 2 plus 2X. All right? So now I know that this is kind of the same thing as the concentration. This is going to be the concentration, but now I'm writing it as kind of a formula with X. All right? Now, maybe you can see what's happening here. This is the concentration of H2 at equilibrium. This is the concentration of fluorine, F2, at equilibrium. And this is the concentration of hydrogen fluoride at equilibrium. This is the ratio of these guys. So what we can do is, and here's kind of everything. What we can do is, remember, this is our equilibrium expression. The concentration of hydrogen fluoride squared the concentration of H2 times the concentration of fluorine F2. And we know that all of this is going to equal 1.15 times 10 to the second. Another way of writing this or thinking about this is 115. So, in fact, let's go through and just say it's 115. Maybe easier to think about. All right, so we have that. Now, this is our equilibriums for these guys. I can go through and put these in for these concentrations. I may not have the exact number, but I know it's going to be 2 minus x, right? So let's go through and write that in. So for HF, it is 2 plus 2x, that's the concentration of HF, squared. All right, that's on top. That's my product. For hydrogen gas, it is 2 minus x. And for fluorine gas, it's going to be 2 minus x. All right? And we know all of this is going to equal 115. Now, maybe you guys can see what's happening here. Now we can just solve for x. If we can go through and solve for x, then we can plug in x for this guy, plug in x for this guy, and plug in x for this guy. Bing, bang, boom. We got ourselves our equilibriums. I know how much of this dangerous hydrogen fluoride gas is around. All right. So let's go through and do this math. I'm going to be honest. The math on this can get a little tricky. It's okay. You guys have been through this. I'm going to try and work through this particular one. But unfortunately, due to the nature of equilibrium expressions, they're all going to be a little bit different for right now. When we get into acids, Kas and Kbs, those are going to be very similar every time, and you'll see why they're very similar. So you can kind of do the same process. But for right now, when we're just learning about equilibriums in general, they could look very differently, and then you have to use different things. So you have to remember like how to FOIL and the quadratic equation and things like that in order to solve for x. So all those math skills that you've learned are going to come out in force right now. All right, so let's go through and solve this. Let's solve this for x. Now, the first thing I'm going to do is I want you to realize that 2 minus x times 2 minus x, that's another way of writing that is just 2 minus x squared. All right. So that means I have a squared term on top and a squared term on bottom. So what we can do is just square root both sides to get rid of these squares. Okay? And for the sake of sanity, I'm going to go ahead and simplify this guy real quick. 115 square root 10.7. All right, that's 10.7. 10.7. Now, I'm going to move this over to minus x here. Multiply both sides by 2 minus x. And then multiply this out. So this is going to be 21.4 minus 10.7x. All right. Kind of clean this up a bit. There we go. Okay. And that is that. Okay. So now I'm going to go through. I'm going to move this 10.7x to the other side and move the 2 over to this side. So 21.4 minus 2 is 19.4. And 2.7x plus 2x is 12.7x. Great. Did all of that. And now divide this by 12.7. And so x will equal, what is this going to be? 19.4 divided by 12.7. About 1.5. 1.5. Cool. So now I know my x is 1.5. I can go back to this thing. I'm going to just write up here 1.5 and erase all of this. Actually, move it up here. So now I know that this is plus or minus. All right, I paused the video, but I forgot to turn it on again. All right, so going, looking through, I noticed something. All of this stuff is 3 significant figures, so let's use 3 significant figures here. So if our x is 1.53, let's go through and do that. So this is going to be, we're going to subtract x, or 1.53, subtract 1.53, and here we're going to add 2x, or 2 times 1.53. So that's 3.06. All right, and so our equilibriums are going to be 0.47, 0.47, and this one is going to be 5.06 molar. All right, so now we have ourselves our equilibrium concentrations. Hooray, we did it. We now can go through and look at our hydrogen fluoride gas and say 5 point something molar, that's a lot. Better make sure the seals are good on the flask so we don't all die. That's the idea behind this. So yeah, this is how you go through and use a rice table. Another thing that you can do is the following. So it's still the same thing. You do your change as before, but sometimes they won't give you the K, but they will give you the equilibrium concentration of one of your guys. So maybe this one. Let's do this one because it's easier. They'll say this at the end of equilibrium, the equilibrium concentration is 1.7. So now you can go through and do a little Sudoku. Okay, we can figure out what x is just with this information in this column. So 2 minus x is 1.7. So what does x have to be? Oh, well, x is going to be 0.3. All right, cool. And once I know 1x, I know all the x's. So this is 0.3, and this is 0.6. And then I can go through and finish off my math. That's 1.7 as well, and this is 2.6. All right. And you can do it this way if you don't know your K, and they give you one of the equilibrium concentrations. Somehow you need to figure out x. X marks the spot, as they say. All right, so let's go through and just kind of review. What's the process here? So one, make sure it's a balanced reaction. You never know when something's not balanced. So you can't never just trust something is balanced. Especially if it's 1, 1, 1, 1, double check. If you see coefficients, you're probably good. At that point, write out the equilibrium expression. You're going to be using it quite a bit, so get in the habit of writing it down. Don't just, you know, trust that you can figure it out on the fly. Write it down. Put it up in the, in the corner. And also underline your KEQ. If they gave you a K, that's the key. K's are key. Same thing with rate constants, that little k. But with equilibriums, K is definitely your key. Go through and list out your initial concentrations. Start writing out this reaction, the Rice table, reaction initial change equilibrium. You'll want to calculate Q. So remember back here, we had initially we don't know which direction this reaction is going. It could have been going this way. You have to go through, find your Q, and think, okay, my Q needs to go up, which means I'm making products, which means I'm heading to the right-hand side. Okay, I'm going this way. All right. Once you have that, you may need to flip your reaction. If so, flip K. You find the reciprocal of K. And write out a Rice table. Write down your reaction as you should, with the correct way it's going, with products reactants. Denote your K. Make sure if you had to flip the reaction for some reason, we have to find the reciprocal of K. Write out your initial concentrations. Then at that point, you should be able to pretty simply find your change. It's always going to be X. Coefficients come down. And if it's a product, it's positive. It's a reactant, it's negative. So, boop, write out your change. And your equilibrium concentrations, you can find your initial plus X form of that. So in this case, it's going to be 2 minus X, 2 minus X, 2 plus 2X. Okay. Now you can input these guys into your equilibrium concentration. Set it equal to your K. Solve for X. This is where it's going to be a little free form. Different equations, different reactions are going to have different equilibrium expressions. You might have a square on top. You might have a square on bottom. You might have something where all of a sudden you're looking at, a cube root or something. I'm going to be honest, most of the time for exams, this isn't a math test. So they try and keep it fairly simple. But sometimes you might need a FOIL. Sometimes you might need to use the quadratic equation. So go through and do that. And typically with quadratic equations, you do find two answers. One of them is going to make sense. One of them, if you get a negative concentration, no, that doesn't make sense. You can't have negative concentrations. One of them will make sense. Then you can do something. You can actually check yourself before you wreck yourself. You can go through and double check your K. Now, I'm going to be honest, some of these, let me kind of go back here. What were this again? This was 0.47. This was 0.47. Whoop. 7. And this was 5.06. No, it wasn't 6. It was 4. No, it was 6. It was 6. Yeah. Okay. So these are our equilibriums, right? What we can do is double check ourselves. We can set these into our equilibrium expression and see if we get something close to this K. Now, remember, like I said before, I like scientific notation. I like scientific notation because I care about this number. I don't really care too much about the base number. I care about the exponents most of the time. Same thing here. So when we do this, if we get like 130 or 100 or even something like, 99, something that's close to on the same order of our K, we're good. there's going to be lots of room for error here. So let's kind of run through this. So it's going to be 5.06 squared over 0.47 times 0.47. Remembering our equilibrium expression. Equilibrium expression, remember, was HF squared H2 F2. All right. So let's go through and run through this real quick. Okay. Oop, come here. Okay. So off on the other side, I got 5.06 squared. This ends up being 25.6 and 0.6 squared is 0.22. And if we go through, finish this out, I get 116. 116.3. So yeah, this is good. This is pretty close. 116. That's a lot closer than I've seen before. Like I said, if it was 100, I would have accepted it. It was like, yeah, it's fine. But yeah, you can go through, do this equilibrium expression with what you calculated, and if you get the same K as they did, you know you did it right, and you can have that confidence that you're right. If you didn't, and you got an extra 10 minutes, go back, redo it, see what you did, see if you maybe you made a math mistake, you foiled wrong or something. And yeah, yep. All right, guys, that's it for tonight. It's spring break. You guys have fun. Watch all my videos over spring break. I will see you guys later. Have a good one.